usually do this chart. If this is our alkyl halide, we have methyl, primary, secondary, and tertiary. React it with non-branched. So this is all the principles you learn in chapter 8. If we have a non-branched strong base, that's an example of like your ethoxide.
Wait, so what's an AH?
Alkyl halide. These are alkyl halides. Really any good leaving group, really. So if we are reacting an alkyl halide with a strong base, but it's not bulky, I guess maybe that's what I should write, is not bulky. And an example would be ethoxide. If it's a methyl, what type of reaction is going to be, what reactions are most likely?
You mean like SN1, SN2?
SN1, SN2, E1, E2. Well, if it's methyl, can it be
Well, it would
E2?
have to be SN2.
Yeah, it's going to be SN2. Primary, we're still favored SN2. But then secondary and tertiary, E2 is favored. So really, if I see a negative charge on an oxygen and it's not very branched, these are the trends I'm looking at here. Now, what if it's a bulky strong base? I'm going to put SD for strong base, like terp butoxide.
No.
For tertiary, it's going to be E2,
And then E2 again.
E2,
And then primary is E2.
and then methyl,
Is E2?
SN2.
Oh, SN2.
Can't have elimination from methyl because
Oh,
there's
right,
no
right.
place to have a carbon-carbon double bond.
Because this is essentially the same chart that we learned for chapters 6 and 7.
Yeah, yeah. And they don't really start teaching it until chapter 8, so I'm not sure. So Brother Sargent teaches it a little bit sooner. So if you have nucleophiles, or good strong nucleophiles, weak bases, examples would be like your cyanide, your azide, your carboxylate, your like all the in chapter 8, like the beginning of the chapter.
It has a table tagging, doesn't it?
Yeah, just like here, all these in red.
These ones?
Yeah, all these guys. I guess it's just SH minus. So any of those from chapter 8, what are their trends going to be?
All of them have a negative charge on them.
They're SN2 for all of them except for the last tertiaries, like might be E2. I think. Just see your book. Yeah, but I want to make sure. I'm just going to start talking about that. Okay, and then we have more what's called solvolysis. So these are negative charged when they're strong neurophiles. Sovolysis is if they're not negative charge. Really, the best way I have to explain it is if they're like solvents, like your alcohol, water, they'll act by sovolysis. I think they go by SN2. I think they go by SN1, like on your other cases. Yeah. Correct. In this one, for secondary, it's always tricky. I'd probably say sometimes it might be SN2. Usually, I think for sovolysis, it's usually SN1. But they're never really clear as which is which. And then if you increase your temperature, what happens?
It increases
The likelihood of it being E2, right?
Mm-hmm.
So I just want to point out, like here, a lot of this, it's not like, oh, strong nucleophile, only SN2 for secondary. Sometimes it might go by E2. There's things that sometimes, like here it's talking about, like sometimes you get 64% went by substitution, 36 went by elimination. So you're gonna have a mixture. And so like if I wanted a reaction and I wanted to make sure it went by E2, I would increase the temperature. If I want to make sure it's more likely to be substitution, I decrease the temperature.
Gotcha.
Okay, cool.
So for that top one, what we're talking about, because it's going to be a strong nucleophile on a primary carbon, it's going to end up being SN2.
Uh-huh. And if it's SN2, what kind of solvent do we want to use?
DMSO.
DMSO.
And it would always go SN2, right? You can't do an E2 on the primary carbon, or can you?
You could. I mean, you have an elimination.
Oh.
The way I like to look at it, if I drew this out here, because essentially this is what our iodoethane looks like, right? I need my nucleophile, which is my CN. It needs to come in here and come from behind and replace the iodine. And the way I like to think about it, whether or not this is exactly what's happening molecularly, helps me remember. The reason why increasing the temperature increases E2, this would be moving faster. Actually, it needs to come from behind. So it needs to be able to get in here to be SN2. If it hits this hydrogen, we're going to have elimination. So you can see when it's just ethane, there's a lot of space. It's going to be easy for it to get in there.
Yeah.
Like you'd have to increase the temperature, which causes molecules to move faster, and then it might be more likely to hit that hydrogen. Whereas if I made this tertiary guy here, we have all these hydrogens around.
Then isn't it more likely to go E2 because it's got
Yeah.
a lot harder time getting in?
Trying to get in here, like it has such a narrower path. Yeah, it's more likely to hit it. I mean, if it's cold enough, you might get some that hit here and have substitution.
Yeah.
But there's a really good chance you even raise the temperature a little bit, and this guy's kind of moving around. Boom, he has all those hydrogens he could hit to cause elimination.
Isn't he most likely to hit?
I guess he has to hit a beta hydrogen, but
Yeah.
you kind of get the point that more hydrogens around,
Mm-hmm.
I mean, he's gonna be more likely to hit. There's more. takes it away. This isn't, I guess I should draw this example. If you have that carbon, if he hits one of those hydrogens,
Oh, okay, yeah.
that's still primary. So that's why it being tertiary. So the more branched it is, the more likely it's going to be elimination over substitution. And then what's your last one?
The last one is 1, 2, 3 chlorine, so
I think it's
looks
like this,
a-
right?
Yes.
So we're seeing a tertiary chloride. So if you see something that's tertiary, what's your,
Oh, I think it doesn't have the other methyl group going up. It's just 1, 2, 3. No.
but does it have two CH3s off of it?
Yeah, so it'd just be one carbon over. Right? Because it wouldn't be 1, 2, because it has 3, and then the 2 branch off of the third.
Oh, you're saying this guy?
Yeah.
Okay.
Sorry.
So this is what our molecule looks like. So if it's tertiary, what's like your instant thought? If it's
E2.
E2, most likely it'd be E2, but what are we reacting with?
We're working with HOCH3.
So if it's HOCH3, it's
So
isolysis, so we're going to think, oh, probably SN1. But anything else, we instantly think E2, but
right.
So how do you know it's like Savolysis?
Because so it would fall under the HOR.
Oh,
Does
it's
it
just
drink alcohol?
reacting with it.
if you see, the way and it's more strong base, weak base, but when I was in OChem, I wasn't very good at like knowing what strong base good, like weak bases, nucleophiles.
Right.
I would say if you see an oxygen with a negative charge, you're gonna think, oh, strong base. So you think these are the trends. If I see an oxygen that doesn't have a negative charge and there's nothing else in it, so I just see an alcohol or water, I'm thinking Savolysis.
Okay.
So I'm thinking SN1 more likely. If I see anything else with a negative charge, like a nitrogen or a carbon or a sulfur, and even a carboxylate, then I'm thinking a strong nucleophile.